Hi guys, this is our first video for AP Chemistry, and we're still going to talk about chapter number 1. We're going to start off with this law of constant composition or law of definite proportions. In terms of our notes, my goal is to get through slide 25. I'll try to go as fast as possible, so then that way if you need to rewind and kind of go back to something that maybe you felt like I went too quick on, you have that opportunity to rewind. If you've got it all and you don't need it, then we're good and you just have to watch it once. So in terms of the law of constant composition or the law of definite proportions, we will credit the law of constant composition for Joseph Proust. And ultimately the definition would be that a compound always consists of the same combination of elements. So water will always be 11% hydrogen and it's always going to be 89% oxygen. But why can I say that? We know, ultimately, that water has a chemical composition of, which water is just the easiest one that we can kind of think about. Water has a chemical composition that we know of, H2O. Okay, so if I know H2O, and I know that water will always have the same molar mass, I know that hydrogen has an atomic mass of 1.001. I know that oxygen has a molar mass ultimately of 16. I know then that the mass of water is going to be approximately 18 grams per mole, or I could say 18 atomic mass units, AMUs. So because of this, I know that hydrogen has approximately a mass of 1, but I have 2 of them. So it's contributing 2 AMUs to that overall 18 AMUs. So I could find 2 over 18, and then if I made that a percentage, so let's actually erase that, times 100, that's going to give me what? It's going to give me 11%, which is saying that hydrogen is always going to contribute 11%. For water in terms of its composition, and that will always be true. I could do that for any compound, any molecule, and I'll see that it's just going to, that's why Joseph Proust gave it credit to saying it's just the law of constant composition. Each element, each atom is going to contribute a very specific amount every time if I'm looking at that same compound. If I look at this water molecule, it's going to be the same as this water molecule. One water molecule will give me 11% hydrogen. Another water molecule is also going to give me 11% hydrogen. So we have these different things in terms of matter, elements, compounds, mixtures. Really basic, we know that an element is considered to be having only one kind of atom. So I have atoms of an element here, but then I have molecules of an element here. And remember that there are 7 of those diatomic elements. And those 7 diatomic elements we consider to be those as each one of those would be a molecule. We have molecules of a compound. We know compounds must have at least 2 kinds of atoms, so 2 different kinds of atoms. And then we know that a mixture could be any element, any compound. It could be 2 different compounds. It could be 2 different elements. So a mixture is just something that we could actually physically separate. Versus molecules of a compound, we may be able to chemically separate those based again on those compounds and pure substances versus mixtures. Okay, you're going to probably see, and again, remember we call these particle diagrams. You're going to see some types of questions on the AP test that aren't going to be necessarily at this level. Instead, you may be given some type of real-world application that looks more like this. They may ask you if something could be a molecule, a mixture, an element, and they'll give you some kind of like background information. So I really like this, this blog, and it's called The Compound Chemist, or the compoundchem.com. And specifically, I just pulled this one up through the aroma of rain because it's a really good question. And one of the facts that they talk about for this aroma of rain is a production of ozone. So ozone is just O3. And ozone, we kind of don't think about it as having really anything to do with thunderstorms, but it has that pre-rain smell that we get before a thunderstorm happens. You're actually smelling ozone, which is really cool. In stormy weather, what will happen is that nitrogen oxides that are up in the upper atmosphere are going to have some type of electrical charge that will split the nitrogen and oxygen. And once those split, oxygen will split off, and then some of the oxygens will come together to form ozone. Once ozone forms, it comes down into lower atmospheres, and that's the pre-rain smell that we smell. But if I look at ozone here, would I classify ozone as a molecule? Would I classify it as an element? Would I classify it as a compound? So if I look at it, what would we classify it as? Well, first of all, I know that it's only one type of element, but I have chemical bonds here, so it has to be some type of molecule. So I would classify ozone as a molecule. And this would be a really good question as like a STEM question that they would ask. They could ask you about dipoles, they could ask you about polarization, they could ask you about intermolecular forces between these two, between this molecule and maybe another ozone molecule, but they may ask you a really basic question to begin with. Identify what ozone would be in terms of a molecule, compound, or an element. So ozone would be a molecule, all of one type of atom, but we see chemical bonds that are present and there's more than one, so that's going to make it a molecule. And I'll post that link for the aroma of rain, so that way you can read more about it if you want to. You, by absolutely no means, have to do that, though. Okay, in terms of matter, I put all of these up here because I think it's just a nice way, a nice array to see what's the difference between liquids, solids, gases in terms of these particle diagrams. So the following are just examples of these particle diagram, or you may hear molecular representation of elements, compounds, molecules, and mixtures. The far left side is going to show that gaseous state, which makes sense. There's more space that's separating them. This middle column is going to represent liquid states. Far column is going to represent solid states. I see that the solid states have more of an organization to them. Liquid states have less organization, more space, little more space in between them, but they're still pretty close together. And then gas is where I'm going to see that really large variable range in terms of space. Okay, so for Monday, I would like you to classify the following. So you have 6 of these different ones that you'll have to classify. I'd like you to classify the following as elements, or mixture, or a compound. If you have a hard time reading these on your paper or on the PowerPoint, let me know, and then I'll try to add like a little description under on your blog, so that way we can identify each of them. But for example, let's just look at this one. So I have carbon here in the middle, there's a C in there, and then that carbon is bonded to 2 S's, so I have a sulfur on either side of that carbon. And I see that if I look around, I have that everywhere. So ultimately, this is just a compound. I have the same compound, a sample of just carbon that's bonded to my sulfur atoms here. Okay, so we've done this one, but I would like you to do these 5, and we'll talk about them first thing on Monday. Same thing with this. So we have to get good at understanding and building relationships. And this is going to be a good way to help us start to build some relationships. So the following diagram is a Venn map that a student drew to show relationships among substances. There are errors, though, in this diagram, and you're probably looking at this and like, yeah, obviously there are errors. But I want you, as the next part of your homework, so you're going to classify those 5 first, and then the next part, I want to know, how would you fix this? If ultimately we're classifying all of these things as substances, fix this for me as a Venn map, so that way it would show the relationships correctly. And then we'll discuss this on Monday as well. Okay, states of matter, we know them. In terms of states of matter, we'll just hit solid, liquid, gases. But we need to take them at a more, we need to take them at a higher level. We need to understand what are the properties and observations in terms of the macroscopic level, and what are the properties and observations in terms of the microscopic level for solids, liquids, and gases. So there's a link here for the states of matter, for the molecular representations of water molecules. I don't know that it's Maybe it won't even open. We'll wait for it to open. Of course. Okay. Well, we'll come back to that. I'll post that link so then that way you can look at those representations. But let's talk about properties at the macroscopic level of solids, liquids, and gases. So we'll title this macroscopic properties. And actually, let me change this to black just in case anybody is colorblind here. Okay, on the macroscopic level, let's first just start off with gases. And some things about gases on the macroscopic level. I want us to also know that, or you should already know that I could say gas or I could call vapor. You may hear those. You may hear vapor as well. But gas has no fixed volume, no shape. So no fixed volume or shape. Okay? And we know it could conform. It's going to ultimately stay in the container that it's in, but it could make that container expand like a balloon. So I could have gas that I add into a balloon. That balloon can stretch based on elasticity. So the container may change based on a gas, but ultimately that container should contain the gas. But the gas has no shape itself. Is gas compressible? It is. So I would say gases macroscopically and their properties, they have no fixed volume or shape, and they're compressible. Okay, in terms of a liquid, and this is again just macroscopic properties. Does a liquid have a fixed volume? A liquid has a volume, or the volume of a liquid, what I want us to know is independent of the container. Volume is independent of the container. Okay, it has no fixed shape. It will just take the shape of whatever container it's in, or it will conform to whatever container it's in. So no fixed shape. And are liquids compressible? They are not. Liquids are going to be considered incompressible. Okay, let's go to solids. In terms of the solid, we know that volume and shape are independent of the container. Volume and shape are independent of container. So they have definite volume, they have definite shape. Independent of container. And are solids compressible or incompressible? Of course, they are incompressible. Ultimately, they will break due to stressors. Okay, these are macroscopic properties, but we also have to think about not just what we can see, but we have to think about what's on that atomic or particle level. So we need to go to macroscopic properties. I'm sorry, microscopic properties. We just talked about macroscopic. So in terms of microscopic properties, gases, we know that they are far apart. Let's just say, I'm going to say far apart. Let's say, we'll just say spaced. So they have a lot of space in between the molecules or in between the atoms. They move at higher speeds in comparison to a liquid or a solid. So we'll say move at high speeds. And again, I'm calling it high speeds in comparison to a liquid or to a solid. They collide often. Based on that kinetic molecular theory, KMT, I know that gas molecules are going to have constant, random, elastic collisions. So they collide. They're random collisions. So they collide, and those collisions are random, and they're elastic. What does elastic mean? Elastic means that they're going to bounce off one another when they collide, and I'm going to keep intact the molecule itself, because we assume that gas molecules are spheres, even though they may not be spheres at all. We assume that gas molecules are spheres. When they bounce off one another, those molecules are still going to stay intact. And then also I'm not going to lose any energy once they collide with one another. An inelastic collision would be where I would have a collision and then I would lose some type of energy. Usually that energy that's lost in an elastic collision is due to like friction or heat. And in a real world that happens, but in our ideal chemistry world, we pretend like that doesn't happen. Okay, so gases, lots of space, move at high speeds. Their collisions are elastic, those collisions are random. In terms of liquids, let's go to a liquid. Liquid molecules are going to be closer together. There won't be as much space separating them as a gas. So particles closer, but still some space. Okay? And in terms of their movement, they move rapidly in terms of how they slide over one another because they're able to slide based on intermolecular attractions, but it's still not as fast as a gas. So let's say for liquids, they can slide due to IMFs, intermolecular forces, okay, or intermolecular attractions. But they're not nearly as fast, of course, as a gas, which we know. Let's also say, because of this, slide due to IMFs, and then let's also add just really quick, packed, tighter, in comparison to a gas. Okay. Solids. Solid molecules have a definite arrangement. Most solids have a very orderly structure to them. It's not necessarily something that's so random. So they have the strongest intermolecular forces that are holding them together. The molecules still move. There's still some type of movement. There has to be. We're not at absolute zero. So we have definite arrangement. And then let's also say that those atoms will vibrate. And then we also will say that they have the ability to rotate. So vibration and rotation can happen for these solids. And vibration and rotation can happen for all of these. But in specifically the atoms for a solid, the only movement they can have is vibration or some type of very small confined rotations. Liquids and gases have the ability to vibrate and rotate in terms of their atoms, but they also have the ability to have some type of translational motion where they can actually move out of the place that they may have originally been confined to. Okay, we know that with states of matter that ultimately changes in pressure or changes in temperature is what's going to cause a shift in that state of matter. So I could go from a solid to a liquid or a liquid to a gas, and that's always going to be based on a conversion from pressure and temperature. Okay, properties and changes of matter. We have physical properties, we have chemical properties. We've heard about this before. Physical examples, boiling point, density, mass, volume, odor, melting point. All of these things can be observed without changing a substance into another substance. So chemical composition must remain intact. Chemical properties can only be observed when a substance is changed from one substance to another. So I'm actually having some type of chemical reaction that has to take place. So like flammability, corrosiveness, reactivity with acid. Anytime you see that keyword reactivity, that's going to give you a big hint it's a chemical property. We can also categorize properties in two other ways. I could say an intensive property or an extensive property. In terms of intensive and extensive, these are going to tell me whether or not I need to include how much substance or how much material I have versus whether or not it doesn't matter how much material I have. So an intensive property is independent of the amount of substance that's present. For example, density. Doesn't matter how much water I have, the amount of water is negligible in comparison for what I'm trying to find here for this property. The density of water is always going to be a set number. This is different from an extensive property, and that's because an extensive property does depend on the amount of substance that I have present. So a really easy example is mass. Mass, if I'm going to a scale and I'm measuring out how much material I need for a lab, if I don't have enough, that's obviously going to be an extensive property. It will depend on the amount of substance that I have. Energy is another one, and mostly because energy is dependent on mass, making it then an extensive property. There's physical changes, there's chemical changes. A physical change is something that won't change the composition. Chemical change is going to be something that will change the chemical composition. States of matter, that's always one that people have a misconception on. And that changes of state, those states of matter, are considered to be physical changes, so don't get tricked up on that. Okay, really quickly, separation of mixtures. We kind of alluded into this already with our conversation in class yesterday. There's filtration, there's distillation, there's chromatography. In filtration, we're simply separating based on particle size. And then in distillation, we are simply using boiling points to our advantage. And this would be a nice distillation setup here, but mostly it's used to take a homogeneous mixture into its components. And then finally we have chromatography, and we're going to be doing a chromatography lab sometime this coming up week. So in chromatography, it's a really cool technique, and AP Chemistry is really pushing for this. In chromatography, ultimately we're just separating substances based on solubility of different solvents. So really we're trying to use polarization here, we're using solubility, we're using intermolecular attractions or forces. It's really trying to take a lot of that chemistry foundational knowledge and put it into one step. How do we use chromatography, or when do we use chromatography? Chromatography is a big thing that's used now for forensics labs. So if people find, if there's like a lipstick stain that's found, they can take a sample of that lipstick, do a chromatogram, and then see what brand of lipstick it is, what color it is. They can go through and see who's buying this kind of lipstick, and maybe that can help eliminate some different types of suspects. Also, we use chromatography to determine the level of pollutants in water. So if you ever work at a water treatment facility, they'll may use some chromatography to do that. We do it anytime we want to test the purity of a substance. It's a really quick, easy, cheap way to do that as well. Okay, so on Monday, we're going to talk about what you had for homework. So we had those 5 compound classifying, either it's an element, it's a mixture, or compound. I also want you to tell me or show me on Monday that Venn diagram. How would you fix that student's Venn map that was clearly wrong? And what we'll do on Monday, we'll get in small groups, and we'll also have a gallery walk to see what everybody thinks, so that way we can have a discussion. When we get done with those on Monday, we're going to go through units of measure. I'm going to fly through this because your summer homework was fantastic in terms of your metric conversions, knowing how to do some types of dimensional analysis. So I think we can kind of fly through this stuff, okay? Everybody have a really great weekend. I will see you on Monday. And if you have any questions on this stuff, just let me know and I'm happy to answer. Have a good weekend, guys. Bye.